After all, they were like stupid.
Oh, yeah.
But has been.
Oh.
It's like, okay. And he goes and sits in the theater. Whatever shoot was last time. Well, maybe they can lose something. If it was students, I said there was
Okay, homework, pages 1 through 4, was with chain rule. Any problems you want me to go over with you? 29, okay. So, first off, recognizing that there is a need for product rule, but then within product rule, there's chain rule. I cleaned it up all the way to this point. You didn't have to, but I think it's good to understand how to get all the way down to all the way to that factored form. So first off, product rule first, because chain rule, there are two chain rules, but they're only impacting a portion of the problem. Again, if you see parentheses over everything, then chain rule comes first. If it's not over everything, then it's going to be another rule that's going to take precedence. So in this case, product rule, we have f prime g plus fg prime. So there's chain rule here. We do outside derivative 2 parentheses to the first power, inside derivative times 2x, keep g, back to f, and then g prime. So outside derivative 3 parentheses squared, inside derivative 6x squared. Do a little bit of cleanup, and then maybe you're at this stage. Now, if this response, any of these options are fine. But I want to talk about how we can get it all the way down to a factored form. The way you can do it is look at these two here and think of these as two separate terms. Okay. Now, what's common between these two terms? They both share. Yeah, let me start from the left here. They both share a 2x, right? The 4 and 18, that's a 2. They both share a 2x. So that's part of the GCF. How many x squared plus 4s do each have? 1. So I'm going to take 1 out from each. How many 2x cubed minus 1 do they both have? 2. So I can take 2 out. So now imagine dividing this by your GCF, and whatever's left over is going to be inside your parentheses here. So 4 divided by 2 is 2. X divided by x goes away. X squared plus x squared plus x squared plus 4 cancels out. This divided by this, I'm left with 1 set of 2x cubed minus 1. And then from the second expression, if I divide my GCF from this, 18 divided by 2 is 9. X divided by x is x. All my x squared plus 4, there's 1 remaining. And then all my 2x cubed minus 1 squared goes away. And if you do it this way, then it becomes a lot easier to clean that up because all your common factors have been pulled out, and then you should be left with a relatively easy expression to clean up. Again, it's not, on the AP exam, it's not required, but I think it's a good skill to know, especially if I don't think you'll ever see a problem as intense as this on the AP exam, because on the AP exam they're more concerned about do you understand the concepts? It'll be more difficult on the concept and it won't be you're just doing a bunch of number crunching, a bunch of factoring. That tends to not be the pattern of AP exams. But this is a good skill to know because now you can match the answer choice a lot quicker and faster from your version if you can just think of it as, okay, I have two messy expressions. I'm going to just take the GCF out from both and then divide my individual terms by my GCF, and then it'll be a lot easier, faster to get it cleaned up with the remaining expression. But, if it was a test or quiz, through response, you can leave your answer in any form, and that's okay. Okay, anything else, page 1 through 4? Let's go to page 5. Page 9. Start implicit today. So explicit equation, these are equations that we're more familiar with. These are nice functions here where most everything that we are going to be doing is in terms of functions where your x's are nicely separated from your y's. There's only one instance of y on the left and then x is on the right. So we call this an explicit equation. This is going to be a nice function here. Implicit is where there's something strange about the y's. Either there's multiple y's or it's y raised to a power or y not to the first power. So for instance, x squared plus y squared equals 16. This is implicit equation. Y is implicitly defined. A lot of times your implicit equations are not going to be functions, but we can still find the derivative of a graph that is not a function. We just have to, we can still find the slope behavior of that graph. It's just potentially a little messier. So if I want to find a derivative of x, my derivative of x is just what? 1. And what we were doing is we're finding the derivative of x with respect to itself. So technically there's a times dx over dx, but because we're finding the derivative of the variable with respect to itself, it's just basically it's not going to matter. And a lot of times, we don't have to include that dx over dx. X squared, same thing. We're taking the derivative of x with respect to itself. So technically it's 2x times dx over dx. But again, we can drop the dx over dx since that just equates to be 1. E to the 5x. This is a chain rule here. E to the 5x becomes the original function. And then times the n-size derivative, 5x becomes 5. And then technically there's a dx over dx, but it just wipes out. Now, let's say we're asking for derivative of y with respect to x. If that's the case, we're still going to do the same thing as before. Y's derivative is still 1. But now we're asking for y's derivative with respect to x. And so that variable is going to have to stay in our expression. So think of dy dx as just asking for y's derivative with respect to x. Same idea here. Y squared becomes 2y. And then we need to ask for y's derivative with respect to x. E to the 5y becomes e to the 5y times 5 dy dx. So basically, whenever we take the derivative involving y, we go through the same rule that we would if we treated like x initially. But because we're asking for y's derivative, we have to include this dy dx because this is acting as a dependent variable with respect to my independent variable x. So here are the steps we're going to take. Anytime you see something strange with the y's, either multiple y's or y not raised to the first power or y raised to anything other than the first power, you know that you're going to have to go through implicit. So first step, take the derivative like you normally would, treat each variable the same way. But each time the derivative of y is involved, we have to make sure we multiply or include the dy dx immediately after that variable's derivative. Next up, from steps 2 through 4 are just algebraic steps. You're just gathering all the terms with dy dx on the left side. I like the left side because I like to have my whatever I'm solving for on the left side, but you don't have to. You can group all your variable on the right side if you wanted to. But I'm going to try to separate them. All the variables with dy dx I'm going to put together on one side, and everything that does not have dy dx I'm going to separate it on the other side. Next up, I should be able to factor out dy dx from each of the terms, if there's more than one term. And then finally, I should be able to divide everything over and then solve for dy dx. Right, let me show you what that looks like. So number one, we have y cubed minus 2x equals x to the fourth plus 2y. This is going to be some curve to graph, but it's most likely not going to be a function because you have something, multiple instances of y's. Y is not by itself. You have y raised to a different power other than 1. But the nice thing is every term is a nice power rule. So we're just going to apply a power rule for each, but we're going to catch dy dx for every y that we see. Okay, before we even start, how many instances of y's do you see? 2. And so that means you're going to be expecting 2 dy dx's. Okay. All right, so y cubed, what's y cubed's derivative? dy squared. We're asking for y's derivative, so make sure you multiply by dy dx. All right, we're done with that term. 2x becomes 2. X to the fourth becomes 4x cubed. We don't do anything special with x's because technically they do produce dx over dx, but we're just ignoring it. Okay. All right, and then 2y becomes 2. Right. So even though the y disappears, we're still asking for something that starts with a y. So we still need dy dx. So now we're done with the calculus. The rest is just algebraic, trying to combine all the terms together. So I'm going to bring those two terms, gather those terms on the left side. Factor dy dx out. And then your final step, divide the parentheses over. And then now you've isolated your dy dx. Any questions? So here's the big picture. The big picture is this is a pretty messy process, but I want to keep reminding ourselves that this is just some curve, and this is just some derivative. So if I give it an order pair information, in return, it's going to tell me the steepness of this curve at that point. So it does the same job as other derivatives. It's just more involved because there's more things going on. So it needs more information in order to figure out the slope at that point. So as a side note, notice how your dy dx needs both the x and y. And the reason why could be, let's say the graph looks like this, right? A lot of times your graph is not going to pass a vertical line test. And the reason why your dy dx needs the x and y is because if it only gets, let's say you only provided the x. Let's say it was like x equals 2, or let me say x equals 1. Okay. Then if you only provide the derivative with x equals 1, it doesn't know which point to choose. It doesn't know, wait, do you want me to find the slope at this point? Or do you want me to find the slope at this point, right? There are two different slopes here. And so a lot of times that's why for graphs that don't pass a vertical line test, it's going to need both the x and y so that it can pinpoint the exact point that you want it to evaluate, and then they can return you the slope that is appropriate. right? So that's why dy dx here, a lot of times your derivative requires more than one variable because you have overlapping points, and giving it enough information, the derivative will know which point you're referring to. All right, so example 2, sine of xy equals 10x. So this is definitely going to be a chain rule. So we have the outside function being sine, and we have the inside function being x times y. So sine's derivative we know is cosine, and then x times y, we got to go through what? If I want to find the derivative, product rule, yeah. All right, outside function first. So sine's derivative becomes cosine. Cosine of parentheses. Good, no changes. Times my inside derivative. I'm going to put a whole big bracket here, understanding that this xy is not the same as what we can't distribute the xy through. This xy is inside the cosine function. So if we want to distribute through later, it's got to be this whole thing. Okay? The xy is not going to combine with these x's and y's. So we said product rule here, right? So f prime times g plus f. I'll treat x like the f, and I'll treat y like the g. Okay, what's f prime going to be? G function, no changes. F function, no changes. Okay, what's g prime going to be? 1, but we're asking for y's derivative, so we also need to include what? dy over dx. Right. So this whole thing is representative of the derivative of sine xy. Any questions? Okay, equals 10x becomes 10. Okay, so we're done with the calculus. The rest of it is just trying to clean up. We would like to get that dy dx by itself, but right now it's stuck inside this bracket with the cosine xy out in front. So the way I can release it is I'm going to distribute this through. So this whole thing, this is one entity here. Okay, so I got to take this and I got to distribute it through. I'm going to create 2 terms. And then once it's nicely separated, I can start moving things around and try to get that dy dx term by itself. If there's any coefficient variable, I like to put it in front of the cosine so it doesn't get confused with this y is clearly outside the cosine function. So I like to put it in front so it doesn't get mixed in with that xy. But you don't have to. You can put the y after. That's just my preference. So now this is more separated. This is like its own thing. So now I can just subtract this over. I just want to, one piece by piece, eventually isolate that dy dx. Right? You divide both sides by x cosine xy. Right, next page. All right, so anybody still need to look at page 9? All right, number 3. Find all the equations of tangent lines for x squared plus y squared equals 4 when x equals 1. So it says all tangent lines, so you can tell that this is not a function, circle here. But you can tell that at 1, it could be here, it could also be here, right? So we basically are expecting 2 tangent line equations, one with a negative slope through this point, and we'll create an equation with a positive slope through that point. So we can find order pair by plugging into the equation. We can find the derivatives, the slope from the derivatives. So let's start with the derivative just to get that calculus out of the way. All right, so we know the derivative is going to help us get to our slope. All right, how do we know that this is going to be one that is going to require implicit? What gives it away? The y squared, yeah. So again, anytime you have multiple y variables, or y is not by itself, or you have y raised to a different power other than 1, those are all indications that, okay, it's probably not going to be a function, and I have to do this additional step of keeping track of my dy dx's. All right, piece by piece here, x squared becomes derivative.
Sure.
So that's y squared. dy dx. And then
Equals 0.
good. I do want to point out that with implicit, sometimes students tend to exclude that number from being impacted. So just be aware that that is a common mistake. Sometimes students just leave that 4 thinking that, oh, that's just that's not part of my derivative process, but it is. Everything is getting impacted. So make sure that you convert that constant to a 0. All right, we want to solve for dy dx here. So all right, so we have our derivative, we have our slope formula. Notice that it needs both the x and y so that it can pinpoint, are you talking about this point that you want the slope, or is it this point you want the slope? All right, let's plug 1 in for x and solve for y, and we're expecting 2 y values because we can clearly see there are 2 order pairs when x equals 1. Right, so let's plug 1 in for x, let's find the order pair so we can get our order pair and then get to our slope and then do point slope form. Take the square root. We get y is equal to plus or minus root 3. So we have 2 order pairs, right? One order pair is at 1 positive root 3. The other order pair is at 1 negative root 3. And then one at a time, we can plug into the derivative to get the appropriate slope. And then do point slope for each. Let me do the first one first. The way that we indicate that we were plugging this into my derivative, right? You can write it this way. You can say dy dx, and then a vertical line, parentheses 1 root 3. Because a lot of times your derivative or implicit is going to require more than just a number. It's not like y prime of 2 or y prime of 3. It's like dy dx of 1 root 3 because the derivative has both the x and y. So that's typically notation to indicate I'm about to plug this order pair into my derivative and I'm trying to evaluate the slope. So this is the slope for this tangent line. And then the slope for the other tangent line it's going to be, the negatives cancel out, so I'm just left with 1 over root 3. And that makes sense, right? We're expecting this to be a positive slope. We're getting a positive number in return. We expect that to be a negative slope. We're getting a negative in return. So here are the two tangent lines. This one would be y minus root 3 equals negative 1 over root 3. That's one tangent line equation. The other one okay, horizontal versus vertical tangent lines. Horizontal tangents, if we're looking at this circle here, horizontal tangents will be lines that, or where the graph is going to exhibit slope 0. So if you're looking for horizontal tangents, you're going to set your derivative equal to 0, and that's going to help you find that location. But more specifically, you're just setting the numerator of dy dx equal to 0. So if any time you want to find a horizontal tangent, you're just going to find your derivative first, and then just set your numerator equal to 0, and that's going to tell you where the graph is going to have that slope 0 behavior. Vertical tangents would be like where the slope is undefined, right? So there's a vertical tangent here, there's a vertical tangent here, and then the way you find that is this is where your derivative is undefined. And the way you identify those locations is you're going to set the denominator of your derivative equal to 0. So numerator of the derivative will give you horizontal tangents. Denominator of the derivative will give you that vertical tangent where the slope is undefined. But either way, we have to get to our derivative first, our derivative equation, before we can look for horizontal and vertical tangents. So number 4, let's find horizontal tangents for this ellipse, and then we'll do a vertical tangent for the ellipse. But either way, we're going to find the derivative first. So go ahead and find the derivative first for number 4. You know implicit is required because there's something different. There's something additional with the y's, right? All right, horizontal tangents. Set the numerator of your derivative equal to 0. X equals what? 0. Now, we're asking for a horizontal tangent line. So anything that's horizontal tangent line has to be y equals, right? Like y equals 2 or y equals 3 or y equals 4. X equals 0 is not going to be your tangent line equation. It's going to be the location of where that horizontal tangent is. So what can we do from here if I want to find the physical equation of those lines? Back into the original, right? Your original is going to give you information about the points or graphs on the line. So plug 0 in for x, back into the original. I get 0 plus 2y squared is equal to 16. Y squared is equal to 8. Take the square root, I get plus or minus root 8. So these are now going to be, we solved for y, but we also created two linear equations, right? There's a, on this ellipse, whatever this ellipse looks like, there's going to be a y equals positive root 8, and there's a y equals negative root 8. And these are going to be the lines of the horizontal tangents that we just created. Number 5, you want to find the vertical tangents. So you don't start from scratch. You can just start from this dy dx. But now, vertical tangents, we're going to now look at what part of the derivative to find it. Set the denominator equal to 0. Yeah. So it's going to occur whenever y is 0, but we can't say y equals 0 as the line, right? Vertical tangents, we're looking for x equals something. So put this back into the original equation, and you should be able to solve for x. So I get x equals plus or minus 4 over root 3, and those are the two lines that are going to skim the surface of the curve vertically. So these are my vertical tangents. Okay, let's do a couple of practice here. Let's go to number 1. Try number 1. And I just want us to be able to look at an equation and know whether there's an implicit involved, right? And again, the way you can tell is there's something different about the y's. The y either feels out of place, or there's multiple y variables, or it's y raised to a different power. Those are all indications that, okay, I gotta think implicitly, and I have to keep track of my dy dx's. We're just gonna do the odds here. So next up, number 3. Careful that knowing that x plus y is inside the sine function, we can't distribute the sine through. This x plus y is stuck inside this, so we got to go through chain rule. Okay, page 11. Try number 5 and 7. There's chain rule for number 5, that e to the parentheses, outside's derivative, then inside's derivative. Number 7, notice that there are 2 instances of y's, so you're expecting 2 dy dx's to pop up in your derivative equation. And then last problem, try number 9. So number 9, I'm doing a little bit of cleanup before I jump to the derivative. Anytime that we can involve expanding, we can avoid chain rule. So I'm going to just bring that 2 down. And I'm putting that bracket outside cosine so that it's a reminder that I'm going to go through the appropriate chain rule process for that cosine of x squared. Again, you see 2 y variables, so you should be expecting 2 dy dx's as you find the derivative. Okay, so 2 natural log of y becomes 2 times 1 over y times dy dx. Outside's derivative, 2 bracket to the first power, cosine x becomes negative sine x. 1 goes to 0, and negative y becomes negative 1 dy dx. We're asking for y's derivative. Now, I do want to point out something about this here. This is, I think, just something that I find to be helpful. Sometimes when I see students, they say d over dx of y, and they just say dy dx, which is fine. I just find that it's visually, it's helpful to put a 1 in front. And here's the reason. The reason why is because, let's say, okay, you're ready to factor that dy dx out, right? I see students factor dy dx out. If there wasn't a 1 here, I see some students forget to have a placeholder and they just put dy dx as 2 over y. But having that 1 there will be that additional reminder that even when I factor dy dx out, oh, there's still something here. There's still that second term there. So that doesn't seem to be an issue. If it was like 2y, students, know that's just 2 dy dx. There's a placeholder for you. But having when it's just a y, and you know derivatives dy dx, having that one there sometimes can be helpful later on when you factor in, it's a visual reminder, oh, I need to remember there's still a one there. It's not, doesn't just disappear. Okay, so tomorrow is your Unit 2 quiz. Make sure you review your derivative rules. Make sure you have your derivative limit definitions, both definitions memorized. Make sure you review your unit circle values. And then product rule, quotient rule, no chain rule, no implicit on the quiz tomorrow. Look over your notes. It's going to look a lot like your quiz review, 4 pages that we went through. So use that to review. Help session tomorrow. I have a meeting at 7:45, so I can only do a help session from 7:15 to 7:45. If you want to come in, I can answer any questions that you guys have. Again, no calculator. And last thing here, if I actually find the derivative of this, and there's A's and B's involved, remember A's and B's are just constant, it's coefficients, right? So what's y prime going to be for this? 6ax, right? Plus 4b plus, good, constants was 0. So just keep reminding yourself, A's and B's are not variables. They're just some unknown constants that just needs to hang out in front. Oh, and your homework, this is homework that's going to be due on Friday. Okay, so no homework due tomorrow since you're going to be studying for your quiz. So page 9 through 13. I'm going to make an adjustment instead of all to make it odds. So page 9 through 13 odds. I'll send out a reminder tomorrow afternoon. But do that. Sure, I like this. Frank, so you have your homework. You don't like. I didn't think it was good. Nobody can. Like so this there's an outside inside portion. No way. That's not outside. Yeah. So that's how. Oh. So that's the same thing you're doing. That is very why I'm not trying to be all so then the so the e is just the derivative of e is just whatever. Exactly, yeah, it's the exact same thing. And then the natural log derivative of that is 1 over 1 over. Or if it's natural log, so if you have a square of this, yeah, pull it down. Chain rule. And then it's just 2.
No, I'm saying like
But if you left it up top, it'll still work.
Yeah.
Have a great day, guys.
What is in natural log 2y? No parentheses. How much do they have? Yes. And then that's actually 1/2.
This, if zero parentheses, this is still understood that that is your parentheses.
Okay, so then what I have to do is change it?
Yeah, it's still changing.
Oh, okay. So that's 1/2.
Two y times two dy dx. Okay, great, thank you. Thanks, man.
How do you know like when it's not working, when it's good? Like, if you're like putting a goal that like I need to.
Not really, I think the only rule that I have is making sure you resolve your negative exponents. But, you know, on the exam, they don't have a specific place to get to. Because once you have your derivative, you can just leave your answer.
Okay.
But on the multiple choice, if it's factorable, sometimes they make you go a little further, so.
That, yeah.
So I think, you know, there's no one right answer. It's good to know both. Sometimes you may want to clean up to the point that you can match the answer. Other times you can leave your answer in extended messy process expression, but still, you know.
Yeah, because I'm just trying to see with like time wise, I don't want to like keep on going and maybe make a mistake.
There you go. Right. So, you know, the strategy on the exam is if you have a messy problem, stop at the first instance that is acceptable and then just move on.
Okay, so then,
So that it means you don't have to multiply. Let's say you have something on the outside, then you have your
Right.
derivatives. You don't have to multiply that back and forth.
The only exception to that rule is with trig. With trig, I just can't leave it in this form. I gotta go one step
Yeah.
further, right?
Okay.
Yeah, that's the only thing.
And then you also just the negative exponents,
Yeah, negative exponent with it.
that's also with the quiz tomorrow.
Yes, that's right.
Okay.
Thank you.
Thank you.
Yeah, all your book bags up front.
Have a great day.
Have a good day.
Honestly, I don't know.
yeah, you should have showed up today. Sweet. You're gonna dig it down. I'll dig it in now. How do you?
What's the? Is it not? It does not have.
Is it three? Three.
I mean,
30.
what's the, it doesn't. If it doesn't have spring. Oh, the first one you have to. Oh, you have to get part of it. Wait, so the numerators. Yes, and if they're equal to each other, then it is and 0.
You forgot about those.
Other words.
Sorry. Make sure all of your phones are up on the wall. And if you have any smartwatches, make sure you have those on.
Mr. Reed, for this, do you want us to flip the DMV and then the parentheses or treat us?
First off, base.
Yeah.
You need help. Grab it from. I'll get you now, folks. Today is Wednesday, the 27th. If you need scratch sheets, come onto any of the shelves. Pick up a scratch sheet.